Alrighty. So we're looking at number 2, and then we'll go and do a power one, probably number 9. We'll see where we go from there. Alright, so if potential energy is described by this function, what are the components of the force F? And just a little big. So we look at our handy dandy reference sheet, right? And we know that, where is it? Energy, the change in energy, which we could relate to our potential energy function here, is the integral of F dot dr, right? And so we're going to integrate this expression and look at it just with respect to x, just with respect to y, just with respect to z. So really, in a sense, we're doing 3 separate integrals of it. So let's integrate. We'll do x first. 2x squared dx, and I'm just bringing it out, and it's going to run out of space quickly. It's going to be difficult today. Plus integral of 5xy with dx plus integral of hy z squared c dx. Right? Just integrating each thing separately doesn't really matter. So here I'm going to have 2/3 x cubed plus 5/2 x squared y plus 8y squared z. With doing it with respect to x. Yep. Because they're not changing, they're not influencing any change in that direction, because they're perpendicular to the other two. Is one way to think about it. So they're constant in the x direction. And then I can do the same for y, and I'm going to take a little shortcut here because I know that 2x is just a constant in y. 5xy dy plus 8y squared z dy dark square 5/2 xy squared plus 8/3 y cubed z. Yep. And I need a y up here. Yep.
So, I got the right answer, and isn't like the force in the direction that you're
Oh, that's right, because it's u.
It's
U equals the integral.
Force to get u.
Yep.
I was thinking
It's not even Friday.
feels like Friday.
Feels like Friday, doesn't it? That's what happens when I don't write down this. because of course we want F, so we need to take the derivative, not the integral, to get it. So derivative of u with respect to x is going to be, that's why I was looking at it going, I thought it got smaller.
Right, I think it's negative.
Huh?
It's negative.
Yes, because it's a change. So you can do a big negative out front. Plus 8y squared z. And that's why I wasn't putting the other thing in there, so. Duh. Oh, wait a minute. That shouldn't be in there. Really? That's like what? Really is last block, isn't it?
Why is there a negative?
Because what we're talking about is the change in the amount of work that would be done to store that potential energy. So the force, think about this, when you're lifting an object up, you're storing gravitational potential energy. And you're applying it, and the force that's actually storing that energy is actually downwards, even though you're doing the work on it.
So it's just a direction.
Yeah. Should be right, but knowing that it's the third try. Nope, I just turned it back on. But my whole screw up at the beginning of class is recorded, so. That means pretty good, I don't even edit it out. Or say, see, I was trying to show you how not to do it.
Classic.
That's recorded too. I know. Alright, so how long does it take a 1920 watt motor to lift a 285 kilogram piano to a 6-story window 15.5 meters above? So power being the rate that we're going to do work. And we have a constant force here because the gravitational force is not going to change much here. We can look at this either as how much work do I need to do get up there, or look at the fact that the work that we do goes into changing the potential energy of it. All right? They both come out the same way, right? Because the work would be the force dot D, and the force would be mg, and the d would be the height, which is also the potential energy, right? Because we can do our free body. So I'm just going to use the power and use that it's use the simplest form of it. Work per delta time. So mgh, what I work. Delta time is what I'm looking for. And so rearrange and get delta time is mgh over the power. 285 kilograms, 9.8 1 newtons per kilogram, and 15.5 meters all over 1920 watts. Since the watts a joule per second, I don't have any conversion to do. That makes me happy. All right. What should be the spring constant? K of a spring designed to bring a big car to rest from a speed of about 60 miles an hour. 65. So that the occupants undergo a maximum acceleration of this. All right. So, car's got, I think it's got a lot of KE, and then I need that to, after all of this, end up, I think, in a spring here. And I'm worried about the power here, right? Because I don't want this maximum acceleration. So I'm also thinking, if I'm looking at max acceleration, I'm looking at net force on them, right? So if I start off with good old Newton's second law here, and so the force on them is going to be provided by the spring, and that's going to be whatever their mass is, and at most I can have in there 5 times 9.81 meters per second squared, right? That's going to be my max force on them. Anything larger, and I've violated it. Okay, so what has to happen in here to go from here to here is actually work. So, and really, the KE the car has needs to equal the work by the spring, right? Which then eventually, that work done on it by the spring stores the energy in the spring. We're really not concerned. We don't care that the energy is in the spring. We just care that it's out of the car, right? So 1/2 mv squared is going to equal the force done on it. And actually, this should be delta KE here. The delta V here, to be completely correct. Sorry, I'm just looking at it thinking what we don't know. Because it doesn't tell us, how the compression of it. But let's see where we can get to without it. That would be work interior to the system. It's changing its kinetic energy. I'm just trying to get my thinking straight. Because the car's got a lot of kinetic energy. We want to take that out of the car and put that into the spring. So I'm thinking of them as the system. And it's the work done on the car that transfers the kinetic energy of the car to the potential energy of the spring. But what I'm feeling like is we're not going to get at the distance needed here because this is going to be,
You know the training block, you know the map. So then plug in for board, solve board.
right. And yeah, and we can say that we know this, and that's our K. I'm calling it delta D. You could call it X. But I don't have any parameter here. Oh, I do. D squared D initial squared plus 2AD. Wow. Try that again. V final squared equals V initial squared plus 2A delta D. Yep, that's making more sense. So, 1/2, we know M, we know ooh, that's going to be nasty, isn't it? Yeah, no, we'll leave it like that. Alright, substituting in there. And we're left with 4A squared M over 2 delta D squared equals K. See if that works. What was my 1250? 1250. My delta V because it told me my acceleration was 5 G's. 101. So I get 20, that 101 kilometers an hour for me is 28.056 meters per second. Fingers crossed. Because K is not constant. That's the screw up I did. Okay. So we'll just rewrite this part. Start right there. So we have M delta V squared equals K. This is delta V, right? That's going to bring up 4. Yes, but see, that's great. You got this problem right. Could you do it again? So, right, but that's where I'm trying to figure out, do it all the steps. Oh, I see what you're saying. I saw it for K, and I really needed that 1/2 K in there.
Power is a no,
That's wrong.
power is what?
Joules per second.
Power is what? I can't get it. Okay.
I mean, I just did a false start.
Problem is here. Back to where I thought it was. Because this A is constant acceleration, right? And our acceleration is a constant. Because they're asking for the maximum acceleration. So if we're going for an average acceleration of 5 Gs, that would be along the lines of what we were doing. But the maximum happens when the force is maximum. All right? And so that's why this isn't working, because we're assuming a constant or an average here of the 5 Gs. And it's actually, so what we could pull here, and this aligns with what Greg was talking about, if this is the average acceleration, we can actually pull the 2 out of here, because what's your minimum acceleration when it just touches the spring? 0. Right? Your minimum acceleration is when it just comes in contact with the spring is 0. And your maximum you want is 5 Gs. Your average would be 2.5 Gs. So, in essence, what you're doing is saying this value, rather than being 5 Gs, would be 2.5 Gs, because that's what the average would be. What that essentially does, the other way to think about that, since 5 Gs is, this is a weird way to say it, but 5 Gs is 2 times 2.5 Gs. The way I was thinking, get rid of that 2 right there, and that gets rid of it here, and that gets rid of the 4 there, and we're back in business. And that'll end up with your A squared times your mass over your change in velocity squared will give you K. Very weird, kind of, but patched together. That was the problem. Think about that as constant. One of those things I tell you not to do in the next If you wouldn't mind throwing a chair up on your way.